Hi guys, this is a video on C++ references. This is intended to be a review. We're expecting that you've learned about references before. As you may know, a reference is an alternative to a raw pointer that we write with the star symbol in C++. So for example, the int star pointer declaration there, that creates what we call a raw pointer. Instead, we could create a reference using the ampersand in place of the star. The second bullet item there shows an int reference using the ampersand symbol. So this is an innovation between the C and C++ programming languages. As you may know, C++ is based upon C with added features. So C does not have references, C++ does, and they added them for a deliberate reason, which was to try to make pointers easier to work with. We've seen from C programming and C++ programming using raw pointers that there are whole classes of pointer-related programming errors that occur when we use these raw pointers, and references were an attempt to try to block some of those from happening. There are a lot of similarities with pointers since references are really intended to be a replacement for pointers. A reference refers to another object. So it is an object in its own right, but usually we think of a reference as referring to another object or pointing to another object. Likewise, a pointer points to another object, and the pointer is itself a thing, but the whole purpose of a pointer is to refer to another object or point to another object. There are some common uses for them. A big one is to pass a large argument to a function without copying. For example, if you pass a large vector or a large string to a function, we don't want to use pass by value because that would copy that data structure in as an argument. Instead, we pass those things by reference or by pointer to be more efficient. Another common use is an output parameter. An output parameter is an argument to a function that really exists for the purpose of getting output out of the function. It's a workaround for the fact that in C and C++, a function can only return one value. Sometimes a function actually creates more than one piece of information. And a workaround for that is to pass a reference or pointer as one of the input arguments, and the function is responsible for initializing those. Finally, a class can borrow another object instead of owning it. Sometimes it makes sense for a class to have a pointer to another object or a reference to another object instead of containing a complete instance of that object that the class owns. One example we'll see in this class is an iterator object represents a location within a data structure. So it has a pointer or reference to the data structure that it's referring to. We don't want to make a whole copy of that data structure. Here's the syntax for a reference. As we saw earlier, a reference is declared with an ampersand instead of an asterisk. And the semantics or behavior of the reference is somewhat implicit. The compiler will implicitly dereference this address when needed as if it was using the star operator for you. So with references, you don't need to write the star operator every time you want the reference dereferenced. The compiler handles that for you. Likewise, the compiler implicitly takes the address of an object when needed, as if the compiler inserted the ampersand operator to take the address of objects to convert an object to a reference of that object. You don't have to worry about these things. So in other words, it's kind of like the star operator, the dereference operator, is automatically put before the variable name everywhere, with the exception of type declarations and when you're passing by pointer. Here's an example that I think might illustrate that better. So this is a function called min-max. It's intended to compute the minimum and maximum of two ints, x and y. So the situation is I have x and y ints. I don't know which one is the min or the max. I want to compute that. This is a pretty common operation, so maybe we wrote a helper function to do this instead of coding this up many times. So the x and y are the input parameters to min-max, and the min and max pointers or references are the output parameters. And the logic is pretty straightforward. It's the same on the left side and the right side. The left side is using pointers, the right side is using references. So we have an if statement that just says if x is less than y, then the min is x and the max is y, otherwise vice versa. In the bottom left, you can see how these functions would be used. So if I have ints a and b, and min ab, max ab are uninitialized, then I can call min max. Notice that we need to use the dereference operator explicitly in min-max. Also notice that we have to use the address of ampersand operator explicitly with the pointer version. Us programmers are responsible for keeping track of those things and putting them in, and it's a compile error if we fail to do that. With the reference alternative over here, we declared min and max as references using ampersand. And we don't need to dereference min and max to assign into them. The compiler implicitly inserts that for us. There's no ampersand here. Likewise, when we call min-max, we don't need to explicitly write the address of ampersand operator. The compiler handles that implicitly for us. So this is more convenient, and it rules out whole categories of compile errors that programmers find to be distracting and annoying. The semantics of references are a little bit different. They're restricted, and the goal of this is to make references safer than raw pointers. One rule of references is that they must be initialized. So if I declare x and y, those are uninitialized because they have no defined input value. Right here, I'm trying to declare a reference to an int, and this will prompt a compile error because R1 is not initialized. There's a rule that a reference always has to be initialized. There's no such thing as an uninitialized reference. This is to try to avoid having uninitialized bogus pointers or references around. The next line here just illustrates how you would initialize this. So this line compiles fine. R2 is a reference to the int x. Likewise, it is not allowed to initialize a reference to null. Null pointers are allowed, and in hindsight, I think we've decided that that's kind of a mistake, that having pointers that might refer to something and might not has caused a lot of bugs and a lot of unneeded work for programmers. So to try to prevent that problem from getting worse, references cannot be null. So you're not allowed to assign a reference to a null pointer or the literal 0. That's just not allowed. Likewise, a reference cannot be reassigned. Once you initialize a reference to refer to a given object, that's it. That reference refers to that object as long as the reference is around. So I assigned and initialized R2 to refer to X. If in the same program I try to reassign R2 to now point to Y, that is not allowed. That's a compile error. So these rules together prevent most of the bugs that we've seen from null and invalid pointers. If you follow these rules, then your references are always initialized to point to valid objects, and they can't be reassigned, so they can't be moved off of that valid object onto an invalid object, and we know that references are never initialized to null. So if you kind of play by the rules here, we shouldn't have any of those kind of errors with references. Technically, if you work really hard, you can break some of those rules. It is technically possible for a reference to become null if you do some tricky stuff with pointers, but it's not really the spirit of references and isn't done often. Finally, we have the concept of a const reference. Const in general in C++ means that something is constant, never changing. A const reference is a reference that does not allow changes to the referred object, meaning it's a read-only view of the object. You're allowed to look at it, use accessors that tell you things about the object, but you're not allowed to use setters that alter the object. This is usually passed as an argument to a function that has no business changing the argument. So if you have a function that needs to look at a particular object but doesn't really have a need to change it, we often pass that reference as a const reference. This is just to be safe because it rules out accidentally modifying objects. Some really tricky bugs happen when a remote piece of code modifies an object that it really shouldn't, and it makes it hard to debug because the code that is responsible for maintaining that object doesn't know that things changed out from under it. So using these const references makes sure that objects only get changed in the functions that ought to change them and nowhere else. Here's an example of breaking that rule that would create a compile error. This is the copy constructor of an array class. We covered this earlier, and it is a copy constructor because the only argument to the constructor is a const reference to another array, and the spirit of a copy constructor is we're supposed to make a copy of that other array but not change it. We initialize our array's size to be the other array's size. That part's fine. Here I'm kind of trying to steal the other's elements. So a copy constructor doesn't take the other object's elements. It's supposed to make a copy of them. But I broke that convention and tried to steal them. So I say my elements is just the other's elements and then set the other elements to null. That line right there will be a compile error because other is a const reference. I'm not allowed to change other, yet here I am attempting to reassign one of other's data members. It's not allowed with a const reference. So this ultimately helps us out. It helps prevent logic errors where we write code that changes something that we shouldn't change.